So I give some homework. I think only a few of you and 8. Yeah, so far, okay, about 9 of you. But I went through some of your answer. I think some of you, I mean, one or two of you have gotten it correctly. But concept entirely correct. Yeah. So 4, 5, 6, 7, 8, right? 6, 7. Okay. 6, 7, and 8. Okay. So some of you have even do 4, 5, 6, 7, 8, which is good. Okay. So for question 6, so find the electric field inside a sphere that carries a charge density proportional to the distance from the origin. So okay. So find the electric field inside a sphere that carries a charge proportional to the distance from the origin. So where k is some kind of constant. So we will assume that this is a solid sphere. Okay, some kind of a solid sphere, and this is the charge density. Okay, so here is we call because it say a sphere, so they never say a shell, a solid, a spherical shell. So we will assume that here is a volume charge density. So volume charge density means that I mean the dimension should be coulomb per meter cube. Okay, volume charge density. Okay, so inside there is, so what we need to do is just we need to find the field inside. Yeah, the only the field inside. So assuming now I have I will define a Gaussian surface. So let's say, assume that now this is the sphere that carry a charge. So sphere that carries charge density rho equals to kr. Okay, r is the radius. All right, and the rate dash circle, or I mean, we imagine now this whole sphere is represented by by one-dimensional circle. So the rate circle, the dashed line, it is your Gaussian surface. Gaussian surface. Okay. So assume that the radius of the sphere is some kind of capital R, and our Gaussian, so I mean our Gaussian radius is rho. So therefore, for inside the sphere, so we can say that rho is less or equals to R. So which is basically indicate that we are evaluating the electric field inside the sphere. So rho V, so which is the charge enclosed by this maybe I should put R prime instead. So R prime, yeah, because I just don't want to confuse the rho for the charge density rho here and the rho for the radius. So this is R prime, sorry. So this is the rho is given as the volume charge density multiply a differential volume, and if we integrate over a volume enclosed by this Gaussian surface. So this is the volume enclosed by this Gaussian surface. So it is equals to the flux, yeah. It is equals to the flux of the flux coming out from that penetrate through the surface of the sphere. So bear in mind, it is a closed surface. So this closed surface enclosing inside the sphere that has a charge density rho. Therefore, and this volume V is defined by the Gaussian surface. This volume V, it is defined by the surface enclosed inside. So we can rewrite this now in proper term as K. So remember K is the constant, rho is K equals to KR. So what is the differential volume for spherical coordinates? So it is R squared sine theta d theta d phi dr. And epsilon naught E. Okay, so magnitude, and because It is a spherical. It is a spherical surface. So the entire area of a sphere, the sphere area, is 4 pi r squared, r prime square. Okay, r prime square. So K, so this is r power 4 over 4, range from 0 to r prime. Here is going to be 2, right? The evaluation of sine theta from 0 to pi, the value is 2. And for d phi, so the value should be 2 pi. So therefore E, so it is K r prime to the power of 4 divided by times pi, yeah, divided by 4 pi r prime. So this is pi. So r prime square. So we get 4 prime square divided by 4 pi epsilon. Sorry, there's no pi anymore. 4 epsilon. Yep. Okay. Okay. So if you look at the answer, it's the same. Yeah. So I just remove the pi basically. So now, if you want to include the direction of the electric field, so since we knew if the charge distribution is symmetrical over the spherical over the Gaussian surface, which is in spherical coordinates, and here we can say that okay, if you want, this is a magnitude, yeah. So bear in mind this is a magnitude. So if you want to include the direction, which is the vector, and also the magnitude, therefore we can put r prime r cap. So this is that means the electric field direction, it is pointing radially coming from this sphere, from the inside. Yeah. So this is the electric field direction inside, from the center of the, I mean, coming from the center of the sphere. Okay, so this is the answer for question 6. Okay, question 7. Okay, so a thick spherical shell with charge density given as rho equals to k divided by r square. Okay, so the range of r, it is between from A, okay, range A to B. Yeah. So this is a thick spherical shell. So that means it's like a hollow shell with a thickness of B minus A. Yeah. So now we are asked to find what is the electric field. Find the electric field in three regions altogether. So the region is inside the shell, in between the shell, outside the shell. Okay, in between the shell, outside the shell. So, so I'm going to use this. So inside, there is no charge density. So the charge density is defined between A and B. Yeah. So this thickness here, basically the charge density, it is within the shaded area. So this area only. Yeah. Only this area. So inside there is no any sort of charge density. So if we define a, a Gaussian surface inside, so if we define, so this red dash circle represent the Gaussian surface. If we define it inside, okay, there's nothing enclosed, right? So by writing the Gauss law for the Gauss law, so for part A, uh, since um, inside the Gaussian surface, there is no there are no enclosed charge. There are no charge densities. Okay. So this implies, so on the charge enclosed is, so where, but charge enclosed is equals to 0 because there's nothing inside. And therefore, this implies, this implies that E is 0. So there is no electric field. So now if I move my circle that enclose a section of So now the Gaussian surface now appear to enclose, let's say, a portion of the uh, charge density. So which is now at R between A and B. Yeah. So greater than A, so which is obviously greater than A, less than B. So okay. So for part B, so for the region where the Gaussian surface in between A and B, greater than A, less than B. So go back to our Gauss law. So this is the charge enclosed. This on the left hand side represent the charge enclosed, and on the right hand side is the flux coming out from the Gaussian surface that passes through the Gaussian surface. So remember, put a circle that represent the closed surface, and the volume represent. I mean, the volume it is defined is that it is the defined volume by the Gaussian surface. So rho v, so is defined here, which is given as k divided by r square. So which is the volume charge density. So dV is the infinitesimal differential volume in spherical coordinates. Okay, I think I don't need to write this because we already know it is a sphere. So straight away we can write 4 pi r squared. Straight away. Okay. So now, so on the left hand side will be uh, k times r. Here is 4 pi. Yep, altogether. So the value of the evaluation of 0 to pi of a sine theta. So the limits. So the result is 2 here. 2 times 2 pi is 4 pi. Okay, there is. Wait, sorry, I missed something here. Sorry. So bear in mind there is from. So I cannot evaluate directly in this way, right? Because the charge density that we enclose here, there's no charge density, right? From 0 to A. So basically, the evaluation is from A to R, right? From A to R. So I have to, so it is A to R, not 0 to A, yeah? So there's no charge density before that. So there's no charge density before A. So there is no evaluation from 0 to A. So it should be between A to R. So this is K times R minus A times 4 pi. Therefore, the magnitude of E it is K R minus A divided by epsilon naught R square. Okay. So if you want to include the vector, then we just remove the magnitude. Okay. So that is for the region between A and B. So what about R is greater than B? So R is greater than B, that means enclosing the entire sphere. So it means that now so for region R, which is greater than B now, so I will write this as I will start from this point. Okay, I will start from this point here. Okay. So the rest basically, I mean, the rest of the starting expression, I mean, the starting point is the same, but only the limits. So we have to we have to take into account. So now, so because I'm enclosing the entire structure, my Gaussian surface is enclosing the entire structure. So as you can see here, so on my left hand side is representing the charge enclosed. So therefore the limits is from A to B, right, of dr. And then 0 to 2 pi sine theta d theta, 0 to, sorry, 0 to pi and d phi, which is equals to um, epsilon e 4 pi r square. Okay. So now, so this represent, okay, so this is b minus a k. So this is b minus a coming from the integral of with respect to dr, And sine theta d phi, the overall contribution is 4 pi. Yeah. So therefore E, the magnitude of E is K B minus A over epsilon naught R squared. So if you want to look at the vector, so just remove the modulus. So that's the answer. So now for part C, we have to sketch. So we have to plot the magnitude of E as a function of R. And for the case of B equals to 2A. For the case of B equals to 2A. So so we have, let's say, so now for R less than 0, so we have E equals to 0, magnitude of E, and between A and A and B, we have E. Um, so we have this term here. So this is a term between A and B. So for so this is K R minus A over epsilon naught R square. Okay. And we have R greater than B. So if I'm going to sketch this now, so this looks like, so starting from 0, so let's say this is the magnitude of E and R. So starting from 0 up until A, yeah. So the electric field is 0. So this is A, okay. And when sorry, this is R squared, right? Sorry. So basically, so the overall, it is basically varies with 1 over r. I would say that. Okay. So the curve here is r minus a divided by r squared, divided by r squared. Basically, so I mean, you can see it as, so the proportionality constant k over epsilon naught as a constant. Let's say I put it as c. So the variation is r minus a. So this is a linear term over a parabolic term, right? So here we can see that the variation is almost similar to 1 over r. Okay, it's almost similar to 1 over r. So for 1 over r, so you should have something like this. Something 1 over r. So until b, if b equals to 2a, so this is a, right? So let's say this is 2, b equals to 2a now. So which is equals to 2a. So now for this region, it is varies with 1 over r squared. So that means it will deteriorate with the distance. So which is something like this. So you deteriorate with the distance. That means it's going to be smaller when this is when r is going increasing. Yeah, when r is increasing. So at this point here, so this should be at, so the value is supposed to be k over epsilon naught. Let's say this is 2a, so it's going to be a over r squared. Okay, so this is the value. So it's basically it's just a sketch. Okay, it's just a sketch. So as I said, the curve is, of course, there's some curvature for this case. So therefore, I mean, we have a linear term and a quadratic term here, but for the part where greater than b, for the part for greater than b, so it's going to be 1 over r squared. So that means the variation of the magnitude of E, it is 1 over r squared. So it's going to be getting smaller as r increases. So the magnitude of E is getting smaller as r increases. So that this is the term. So this is the curve for part C. Oh, sorry, for part D. Sorry, not part C. So AB. So this is a C part and D. Okay. So question 8. So a long coaxial cable shown in figure 2 carries a uniform volume charge density rho on the inner cylinder radius A and a uniform surface charge density on the outer cylindrical shell of radius B. So this surface charge density, this surface charge is negative. So on the outer is a shell, right? So it's a negative surface charge density and is of just right magnitude that the whole cable is electrically neutral. So that means the volume charge, the total charge carried by the inner rod, by the inner cylinder, the solid cylinder, let's say Q. So the total volume charge, I mean, basically the whole volume contain charge Q, positive charge Q, and the total surface charge on the outer is negative Q. So this is what it means. So it says that this surface charge is negative and it is of just the right magnitude that the cable as a whole is electrically neutral. So find the field in the tree region. So first we need to find for um, for cylinder, which is, I mean, for radius, which is between A and B. Okay, we may not have all the time, so I will just perhaps, if I can maybe show you A and B. So for, let's say S is my radius, let's say, which is less than A. So which is inner, which is the inside, which is inside the inner cylinder, solid cylinder. So I will straight right away. I will right away straight. So rho dV. So for a cylinder, then the Gaussian surface should be a cylindrical as well. So enclosing the now is as you imagine that the Gaussian surface enclose the inner cylinder, and therefore, so here we have rho is so okay. So dV so is this is a constant, okay. So is R sine sorry R dr d theta d phi, right? And epsilon E sorry, there's no d theta, sorry, my mistake. So it's d phi dz, okay. So this is the volume differential of dv, and the limits for dr is we can 0 to r for r dr. D phi is the limit 0 to 2 pi, and we can arbitrarily say that okay, the Gaussian cylinder, the Gaussian surface of the cylinder has a length L, so we can just put length L, okay. So same goes for uh, surface. Yep. So this is d phi 0 to 2 pi and dz 0 to L. Okay. So this is r squared over 2 uh, 2 pi L. So 2 pi L as well. Okay. So therefore E is rho r over 2 epsilon. Yeah. So that's the magnitude, and we want to express it as vector. So this is rho r over 2 epsilon with the direction is radial. So remember this is the radial the radial direction for cylinder. Okay. Um I should use S, yeah. I shouldn't use R, yeah. Sorry. I should use S. Okay, so that's it. Okay. Already time's up. So I will talk to you in the next class. So I will save this. I will post it in the Google Classroom later. So I will see you in the next class. Sorry, Kaibun. All right, thank you.